Okay, so we want to be able to write an equation of a rational function from a graph. We need to be able to find the vertical and horizontal asymptotes of a rational function. And we need to be able to sketch a graph without a calculator, or at least have some idea of what it looks like, okay? It isn't so important you get it exact, but you got to be able to at least know what it looks like, okay? And all rational functions are functions that have a denominator, a numerator and denominator that's not a variable. I mean, well, I guess technically, I mean, if I had x plus 1 over 2, that's not really a rational function, because I can rewrite that as 1/2 x plus a half. And that's a line, that's a linear function, so that doesn't count. But if I had something like 2 over x, that's a rational function. I get a variable in the denominator. I mean, I could have 2x plus x, even though that simplifies, it's still a rational function because it's something more than just y equals 2. Okay, there's something happening in this original function. X equals 0 isn't included in the domain, and there's things that will happen. That's what we're going to explore in a couple of these examples. Okay, so first off, we're going to talk about that second learning target, the vertical and horizontal asymptotes. I'm going to start with the vertical. So I've got these two rational functions. The g of x is a little bit easier just because it's already factored. Let's talk about the first function, f of x. When I'm looking for vertical asymptotes, that's places where x isn't included in the domain. Okay, and what happens there is the graph will look, you know, whoops. You can have something like a dotted line. I mean, you don't have to draw the dotted line, but that's a place where the function will approach, but it'll never quite reach. And a horizontal asymptote is also a place where a function will reach and not quite get there. It's asymptotic. Now, one caution with that is it is possible, like suppose I had this graph, here's the x-axis, it is possible to have a function that will dip down below an x-axis, below an asymptote, but in the long run it acts asymptotic, okay? So just because it does cross a supposed asymptote once doesn't mean that it's not an asymptote in the long run. Okay, because really with asymptotes we're talking about long-run behavior. For horizontal asymptotes, we're talking about long-run behavior. Vertical asymptotes, we're talking about what happens at a point or at a certain value of x, usually, okay? Or whatever variable they're using. So how do we find vertical asymptotes? Well, vertical asymptotes happen in the denominator because we can have some number on top. We can't divide by 0. Okay, so what I want to see is I'm looking for this first function. I'm looking for when does x squared minus 7x minus 8 equal 0. Well, this is a quadratic equation. We could use quadratic formula, but this one factors very nicely. Okay, so that tells me something's this expression is equal to 0 when x equals 8 and also when x equals -1. And if I go back into my original function here and I substitute both of those in, you don't have to do this part. I'm just showing you why this works. So if I substitute in 8 squared minus 4 over 64 minus 56 minus 8. Well, that's going to be what? 16 minus 4 is 12, and we know the denominator is 0. Can't divide by 0. 8's not in the domain, so that tells me a vertical asymptote will be at x equals 8. And if we choose to use x equals -1 in our expression, -1 squared is 1, which would give me -4 and -3 on top. And the denominator, I'm going to get -1 squared is 1, plus 7, minus 8. So that's going to be 8 minus 8 is 0. Can't divide by 0 again. So that tells me there's a vertical asymptote. And when you write vertical asymptotes, it's certainly appropriate to write VA to stand for that. But if they ask you for the asymptote, write it x equals 8 and x equals -1, okay? Unless my open math asks you to do something else. Okay? So think about this. Now let's look at the second equation. They've already factored the denominator for us. Okay? I want you to look at that. Stop the video, look at that, and see if you can't decide where the vertical asymptotes are happening. Okay, so I'm going to pretend you actually did stop this recording and looked at this. So I'm looking, I don't care about the numerator. I just care about this denominator. The 3 doesn't have anything to do with it. That'll never be 0. But I do know when x equals -1, something's happening, and when x equals +3, something's happening. And if I were to replace each of those into this original g of x function, I would get, well, if I did -1, what is that? 2 times 2 is 4 over 0. And if I substitute in the 3, that would give me, actually, I'm sorry, won't that give me, yeah, no, I was right, 4 over 0. And x equals 3 would be 6 times 2 is 12 over 0. So in both those cases, I can't divide by 0. Okay, so vertical asymptotes, those are the 2 vertical asymptotes there. Okay, now comes the sneaky part. And actually, you're going to spend more time with this in calculus, at least the beginning of calculus, than you are right now. So it's kind of crucial to understand this idea and to recognize what's happening here. Same deal, they're looking for the vertical asymptote. So I'm going to look at the denominator. I'll let you stop the video and factor that and try to figure out the zeros. Okay, so I'll factor it now that you've got this recording going again. So that factors to x plus 3 over x plus 1. So it looks like something's happening at -3 and something's happening at -1. And typically we don't have to do anything more than that. There's a special situation going on here. If you look back at this original equation, I see I got a common factor on top and on the bottom. If I were to replace x with -3, I'm going to get -3 plus 3 over -3 plus 3 times -3 plus 1. That's going to give me 0 over 0, which isn't a number over 0. So this is a special situation. In calculus, you'll learn this is called an indeterminate form. You know, if I could spell indeterminate, something like that, form. When you get 0 over 0 is the first one you'll see. So when you see that, that tells you something else is going on. Now, if you were to, I won't fire up a calculator, but if you were to graph this right now, you would only see, well, I'm going to fire up a calculator. So here's a graph of that function, okay? And what I'm seeing here is I can get a value for x. I can't get a value with x equals -1 because that's where that asymptote, that vertical asymptote happens. If you remember, we have this x plus 1, so that tells me there's a vertical asymptote happening at x equals -1. So, but if we go to where am I? If we go to this graph, we know -3 isn't in the domain either, and you see what happens. And this graph and calculator shows us a nice job that there's an actual hole in the graph right there. And that's how when you get 0 over 0, that indeterminate form, that's what's happening. There's a hole in the graph at that place. Okay, so it's something you got to check for and look for. Okay, so I hope that helps. Okay. So now we're supposed to, another one of our learning targets was to be able to sketch a graph without a calculator of a rational function. Well, a couple of things that we want to address before we tackle that, and you might have talked about this a little bit in college algebra, is we know there's a vertical asymptote happening right now at x equals -1. Right, so if I were to graph that, I know x equals -1. I would probably want to have a vertical line, a dotted line to show that asymptote happening. Okay, but then here's where it gets a little bit trickier. Not a lot, but some. Okay, I know that I can't have a number over 0. But having 0 over a number is perfectly acceptable, and that's what we're going to look for. We want to look for, because this expression is equal to 0, and if I know that f of x equals 0, whatever x is a 0 or a root, right, where it crosses the x-axis. So when you're looking for zeros, you just want to look at the numerator. You don't really care about the denominator. I mean, paying attention to the wholes. So this equals 0 when x equals 2 and when x equals -4. So on my graph, I can plot a point at 2, I can plot a point at -4, and then one of the learning targets was this idea of a horizontal asymptote. So if I were to expand this equation all out, and you kind of already done some of this, so I don't think I'll do it right now, but I know the numerator is going to have a leading term of x squared, right? And I know the denominator is going to have a leading term of x squared. And when x goes out to infinity, when x goes out to positive infinity, it works out that all the other terms, well, let's write it out. Plus 2x minus 8 and plus 2x plus 1. If I go out to a really large number, 1,000. 1,000 squared plus 2 times 1,000 minus 8 over 1,000 squared plus 2 times 1,000 again plus 1. Well, the minus 8, when you're talking about 1,000 squared, isn't that going to be, what, 1,000,000? 1,000 times 1,000? 10 to the third times 10 to the third is 10 to the sixth, which is 1,000,000. So when I'm way out at 1,000,000, or 100,000,000, or whatever number you want to pick, some large number, the 2 times 1,000 or 1,000,000 or whatever minus the 8, these terms just don't affect the answer that much. And since these 1,000 squared over 1,000 squared is the same number, that's going to be pretty darn close to 1. Okay, so that tells me when I go out to very large values of x, out to infinity, there's going to be a horizontal asymptote. So the horizontal asymptote is going to be y equals 1. And if I were to go out, ask myself what happens when x goes out to negative infinity, and I'm going out this way to negative infinity, well, this term is going to be squared. It's going to be positive again. So that would tell me that the horizontal asymptote to the left is the exact same number, y equals 1. Alright, so I know somewhere that this graph is going to approach. It could be approaching it from above, it could be approaching it from below, and the same thing here. I'm approaching y equals 1. And then I got to ask myself what's happening in the close. I know there's a vertical asymptote here, so it could be like this coming up from that, it could be like that coming up from the left. And then I got to decide what's happening here. And what I can do is I can just pick some points. What if I use 0? What if I use x equals 0 and get the y-intercept? Well, if x equals 0, isn't that negative 2 times 4 over 1, which is negative 8? So that tells me that what's happening here. And I could pick some more points, but this graph coming from the right to that asymptote is probably looking like this. Okay, and if I were to pick negative 2, say, negative 2 would be negative 4 times positive 2 over 1. Well, that's going to be a negative. So that tells me this is coming. So I'm thinking this graph looks something like this, almost like a inverse reciprocal squared function. Okay, it's been shifted. Okay, so that's kind of what you got to do. You can start looking for patterns. and picking points. Here, I'm going to stop this video and then keep recording later.